In this class, we will start our discussion from, uh, we will enter into our module 6, and then we got module 5 also. Then after finishing this module 6, we will discuss module 5. So module 6, convex programming problem, CPP. Then in that we will discuss one method, that is exterior penalty method, to solve convex programming problem. With an example, we will solve it. And before entering into our discussion, you should have the basic knowledge about what do you mean by a convex function. A convex function. So actually, in our BTech also we have studied this convex function. What do you mean by convex function? That is, in a short concept, graphically we can represent a convex function, say f of x, like this. The convex function is having like this shape. Okay, so we will we will have a number of examples for this convex function also. And so the definition of a convex function is like this. A function f of x we have, for capital X we have f of x, and it is said to be a convex if for any pair of points x1 and x2. That means we are considering 2 points x1 and x2. That is, these 2 points are vectors x1 and x2. So x1 is x1, x2, x3, etc. xn. That means it is n dimensional space, and for first point these are the coordinates. So in order to have the distinction between the first and second point, I am writing it as 1. And x2 is same. We have the coordinates same, x1, x2, etc. xn, and for the distinction between first and second points, we have here 2. So second point. Okay, and we are defining a scalar quantity lambda, and lambda can take values in between 0 and 1. Okay, and so this is yes. So the function f of x is said to be a convex function if f of lambda x2 plus 1 minus lambda x1 is less than or equal to lambda times f of x, sorry, f of x2 plus 1 minus lambda times f of x1, of x1. So in order to understand this, what do you mean by a convex function graphically, we can take an example. So let us consider f of x to be a one variable function, f of x to be a single variable function. So f of x, and so we have the axis, okay, like this. This is x-axis, x represents x, and this axis represents f of capital X. And our f of x looks like this. Okay, so this is our f of x, and I'm considering 2 points. Okay, x1 here, x2 here, and this point, the line joining these 2 points x1, x2, the line segment is having an arbitrary point. Let us say it is x, and this x is, capital X is dividing this line segment in the ratio lambda is to 1 minus lambda. Okay, so this x1 to x is lambda, and x2 is 1 minus lambda. So that means lambda is some 50% of this line segment, means 50-50. You will get the midpoint here, x. So like that, and lambda is lies between 0 and 1. Okay, some fraction, right? So then what happens, this x1 corresponding to x1 point, we have here, we have the point f of x1, and corresponding to x2 we have f of x2, this point, and corresponding to x, if you substitute, we have f of capital X, this point. Okay, so, and I have a line, I'm considering a line joining the f of x1 and f of x2, which are the 2 points on my f of x graph. So like this, yes, I have, this is the line joining the f of x1 and f of x2, that is 2 points on the f of x graph. So that, and corresponding to x, I have, on this line, I have the point P. The point P is given as, is nothing but, actually this is lambda, and this is 1 minus lambda. So in the same manner, if this x, right, is, if this x divides in the ratio lambda is to 1, lambda is to 1 minus lambda, then it is also true that this inclined line line segment. Okay, on that line segment we have the point P. So that point P divides the line segment in the same ratio, lambda is to 1 minus lambda, lambda is to 1 minus lambda, lambda is to 1 minus lambda. Okay, so that you can prove. So I'm not going into that proof, but you can prove it. So the lambda is to 1 minus lambda, the ratio of division is same. Okay, so in that case we have the point P, that is nothing but here we got lambda into x2. So this x, okay, this point line segment x1 x2, we can write this x as x is equal to is lambda into x2 plus 1 minus lambda into x1. So x into sorry, this is lambda into x2 plus 1 minus lambda x1. Okay, so this is what x. So similarly, in the same concept, we can write the point P also. That point P is given by f of this this is lambda and 1 minus lambda. So we cross multiply and sum. So what you will get is lambda into f of x2, okay, plus 1 minus lambda into f of x1. So that is nothing but your point P, okay, and that is our point P, point P. At the same time, we can have the expression for f of x also. So f of x will be is equal to f of, you substitute for capital X, that is nothing but f of lambda x2 plus 1 minus lambda x. So 1 minus lambda into x1. So this is x. So this is equation 1 and this is equation 2. Okay, so what the definition of a convex function is saying that this equation number 1 and equation number 2, if you compare, then this equation 2 must be always less than or equal to equation 1. Okay, so that means equation 2 is nothing but your f of x. That means it is, in general, you can say any point on the graph f of x, any arbitrary point on the graph f of x. So that is what equation 2. But and equation 1 is the point P, that is nothing but actually in general you can say the line equation of line joining the 2 points f of x1 and f of x2. So you can conclude that if the segment joining the 2 points, if the segment, the line segment, a function capital f of x is said to be a convex function if the line segment joining the 2 points, okay, 2 points means x1 and x2. So these 2 points and lies the line segment joining the 2 points x1 and x2 lies entirely above or on the graph of f of x. Okay, that is the what you mean by that definition of a convex function. That means in order to have an idea that whether the function f of x is a convex function, what you have to do is you have to consider 2 points. Let us say this is my x1 here and this is my x2 here. Okay, and then you join a line, you draw a line joining these 2 points x1 and x2. x1 and x2. Okay, if this line segment joining these 2 points x1 and x2, sorry, this is f of x1 and f of x2. Okay, if the line joining the line joining the 2 points f of x1 and f of x2 on the graph that lies above the f of x graph, that lies above the above this graph, above the f of x graph between f of x1 and f of x2, then such kind of a function is known as convex function. So that is what I mean by this definition. That means, yes, this definition, that is f of lambda x2 plus 1 minus lambda x1 is less than lambda f of x2 plus 1 minus lambda f of x1. So we have meaningfully defined less than value. What if this equal to, when it comes equal? So if it is this condition equal, if the equality condition comes, then also our our function is, it can be considered as a convex function like this. For example, I am taking 2 points here and here. Okay, let us say this is my f of x1 new and f of x2, and I am joining the 2 points by a line segment. So this line segment is approximately coincides with this f of capital X, f of x itself. Okay, in that case also you can conclude that the objective function, sorry, the function f of x is a convex function. Now let us understand whether the function, okay, like this, the function, sorry, like this is whether it is a convex function or not. So again, you have to consider 2 points on this graph. Let it be, this is our f of x graph. So you have to consider 2 points. I'm considering 2 points like this. This is f of x1 and this is f of x2. Or you can say this is just okay f of x1 f of x2. Instead of that, this is y1 and y2. Now you join these 2 points and you will get a line segment. Okay, and you observe the graph under this, below this line segment. If it is below, then if you take any arbitrary point on this f of x, let us say y, okay, y, so this y will be always less than or equal to this line segment f of s lambda f of x1 plus 1 minus lambda f of x2. Okay, now if you take 2 points like y1 and y2 here, so what happens is the line segment joining these 2 points y1 and y2 exactly coincides with our f of x graph. So in that case also you can say the given function is a convex function. So in that manner you can you can conclude that whether the function f of x is a convex function or not. So next, if you consider a sinusoidal waveform, let us examine that whether a sinusoidal waveform is a convex function or not. So like this we have the sinusoidal waveform. So I am considering 2 points on this sinusoidal waveform. Let it be, here it is y1 and here it is y2, and I am joining these 2 points, okay, by a straight line. So what you got is this line segment. If you consider, okay, it is always below the below our waveform, our f of x equal to sin x graph. So it is not a convex, okay, it is not at all a convex, because it is, this line segment is below this f of x graph. So that means if you take any point f of x equal to, on this f of x equal to sin x, then that lies above the line segment joining y1 and y2. So in that case, that is nothing but the violation of our convex inequality construct. So in that case, this we will declare that the sin x, f of x equal to sin x, is not a convex function, but provided that up to 0 to pi I am defining. So up to 0 to within this limit, 0 to, that is 0 less than or equal to theta less than or equal to pi, within this theta limit I will get that this sin x, f of x equal sin x function is not a convex function. Now if you consider pi to 2 pi of the same sinusoidal waveform, and if you consider two arbitrary points y1 and y2, or two any pairs of arbitrary points y1 and y2 in between this range theta less than or equal to, sorry, pi less than or equal to theta less than or equal to 2 pi, in this range if you consider any pairs of points, and if you join these such two points, if you join, you will get a line segment, and this line segment will be always lies above the sin x graph between y1 and y2. Always it lies above the f of x graph. F of x equal to sin x graph, always, okay, always between y1 and y2. So in that case, it satisfies the condition for a condition for a function to be a convex function. So we can say that f of x equal to sin x is a convex function between pi less than or equal to theta less than or equal to 2 pi in this range of theta. Okay, so that is what the definition of a convex function. So this is just for your information. Now you will get a conclusion in this convex function, that it can be seen that a convex function is always bending upward, okay, like this or like this, okay, or like this. So hence it is apparent that the local minimum of a convex function is also the global minimum of that function. That means local minimum we have, for example, in this case, this is suppose we have f of x curve like this. So we have we have minimum values for these functions in at this point, and at this point we have, and at this point. So these are all are together known as the local minimum. But the global minimum can say global minimum is minimum of these local minimum. Okay, so if you if you apply that definition to a convex function, it is only having a single local minimum. So and that itself is its global minimum also. Okay, then we are moving on to what do you mean by a convex programming problem, CPP. Actually, this convex programming problem is nothing but your non-linear constraint optimization problem. Non-linear constraint or constraint non-linear programming problem. Okay, constraint non-linear optimization problem. So convex CPP is nothing but this constraint non-linear programming problem, and this is having the form minimization Okay, minimize f of x. That means we have CPP standard form, minimize f of x subject to the constraint which is gi of x less than or equal to 0 for I equal to 1, 2, 3, etc. up to m. That means m number of linear inequality constraints are there. Okay, so this is our standard form. So for a constrained nonlinear programming problem, the constraints may be equal, may be equality constraints like hk equal to 0, where k varies from 1 to etc. up to p. Okay, it can be equality constraints as well as inequality constraints like less than or equal to 4. But the convex programming problem is a special case of nonlinear constraint optimization problem in which the standard form is minimization only and minimize f of x, our objective function, subject to only the linear inequality constraint which is of the form less than or equal to 0 form. Okay. So the standard form of CPP looks like this, that is find x which is equal to the n which is defined in the n dimensional space, and it is x1, x2, x3, etc. xn transpose, which minimize f of x subject to gj of x less than or equal to 0, and j can take values from 1, 2, 3, etc. m. So that means m number of constraints are there, that is of the form gj of x less than or equal to 0. Okay, so this is our CPP, that is convex programming problem standard form. Now we will discuss the method, one of the methods of solving the CPP convex programming problem. So that method is known as exterior penalty function method. Exterior penalty function method. So this method is used for solving general nonlinear programming problems. Actually, this CPP is a special condition or a special problem of nonlinear programming problems. Okay, which is constrained nonlinear programming problem. Okay, so we can use this exterior penalty function method for this CPP solving also. Okay, and in this method, what we will do is we will formulate, actually the CPP is constrained nonlinear optimization technique, but we will formulate this constrained nonlinear optimization technique into a series of unconstrained optimization techniques or problems. That means a sequence of unconstrained. Constrained will be transformed to unconstrained minimization techniques by introducing a new term to the original objective function f of x. Okay, and that new term is known as penalty function. That new term is known as penalty function. Okay, so our let us consider this standard form of our CPP. That is, find x vector x that is equal to x1, x2, x3, etc. xn transpose, which minimize f of x subject to gj of x less than or equal to 0 for some values of j, 1, 2, etc. m up to the total number of constraints. And now let us assume that there exists on iteration process, okay, while iterating. As the iteration goes on, at some point of time there exists at least one constraint, let us say gk, okay, gk, for which our solution, we found out the solution for kth iteration, let it be xk star, okay, our optimal solution. But at this point of time, this xk star, when you substitute to gk, that is kth constraint, if you substitute, okay, you will not satisfy, you are not satisfying gk less than or equal to 0 condition. Okay, that means if you substitute xk star, let us assume that gk is greater than 0. That is what you mean by the violation of this constraint, gk less than or equal to 0. That means gk greater than 0. Okay, so at this point, what we will do is we will append or augment or add a penalty a penalty which is for violating some gk constraint, okay, to our objective function. So what we will how we will proceed in CPP is, I will repeat once again. If you have this standard form of CPP, okay, right, then what we will do is we will optimize, we will treat this CPP as our f of x as our nonlinear unconstrained, okay, unconstrained nonlinear programming problem. We will treat it as treat this like that, okay, and we will proceed. So we have several methods for solving this kind of problems that we have already studied in our module 4. Okay, then at some point of time, and we will check, or and we will get the optimal optimum solutions like xk star, like x1 star, x2 star we will get, okay, in general xk star we will get, okay. And then what we will do is we will substitute in this constraints, whether and we will check whether it is satisfying or not, whether the given constraint is satisfying or not with this with our optimum solution. Okay, and at one point of time, or one at one point of iteration, we found that this xk star is not satisfying some constraint gk less than or equal to 0. That means gk, if you substitute xk star in gk, we will get gk greater than 0. Okay, in that case, what we will do is we will append or augment or add a penalty for violating the gk constraint to our objective function. Yes, so that our nonlinear constrained programming problem now becomes a unconstrained nonlinear programming problem, or so that or a sequence of, you can say, in other words, you can say a sequence of unconstrained minimization technique problem. Okay, so that after augmenting or addition, the f of x becomes like another new function that is notated by phi, and phi of xrk, and that is defined as f of x plus rk sigma j is equal to 1 to m, and this is another kind of a notation. Okay, gj of x power q. Okay, where this rk is a non-negative integer, sorry, non-negative value known as penalty parameter. Okay, and it is a non-negative integer, to be specific. And the bracket function is defined as, that means this bracket function means this function. Okay, bracket function is defined as, that is gj of x equal to maximum of gj of x. That means our constraint gj of x and 0. Maximum of gj of x, that is our constraint, and 0. Okay, that means if gj of x less than or equal to 0, that means this constraint is our optimum solution is satisfying this gj of x less than or equal to 0. Okay, that means you can choose a maximum of gg of x and 0. That means this will be a negative value. Okay, and maximum of a negative and 0 will be 0. So that means this f of x plus this penalty penalty term becomes equal to 0. Okay, but we have this in we have added this penalty function or penalty term because this gg of x is greater than 0, right? So this maximum of gg of x 0 will be gg of x itself. Okay, so and yes, so this is the bracket, the explanation of this bracket. And this q is again an integer, and in our case we will take q is equal to 2. Okay, that means square only we will take. Okay, and so it can be seen from equation 1, that is this equation, as you can see, that the effect of the penalty term on the RHS is to increase phi of x rk in proportion to the qth power of the amount by which the constraints are violated. That means if the constraints are violated, then the objective function has to pay the penalty for that. So the penalty parameter, how much is defined is decided by this rk. Okay, this rk value as well as this q value. So okay, so that means if more than one, that is more than one constraints are violated, then that much number of penalty term will be added or augmented to our objective function f of x, so that phi of x rk will be increased. Okay, in that way we will formulate our CPP. Okay, so this there will be a penalty for violating the constraints, and the amount of penalty will increase at a faster rate than will the amount of violation of constraint for q greater than 1. Okay, as the power of q increases 1, 2, 3, then the penalty, the rate at which the penalty is added, okay, is the penalty added will increase. Okay, so this is the reason why this formulation is called the penalty function method. And the so that this constrained nonlinear programming problem is now formulated as a unconstrained nonlinear programming problem with this penalty by adding or augmenting this penalty. Okay, so that you can solve this by our unconstrained optimization technique. So in this way, what happens is our optimum solution can be find out by formulating the constrained CPP, that is our CPP, by formulating this CPP by a sequence of unconstrained minimization techniques, SUMT. Let us consider a simple example in order to understand what we have discussed so far. So our convex programming problem is like this. Let us say, suppose we have the problem minimize x subject to 5 minus x less than or equal to 0. So is this a convex programming problem? Let us check. So the objective function here f of x is equal to x. That means like this. F of x equals to x means like this. Okay. So that means if you take any arbitrary points y1 and y2, okay, any arbitrary points, arbitrary pair of points y1 and y2, and if you join the 2 points by a straight line, a line segment, then that exactly coincides with our graph or our objective function f of x. So by definition, it is by definition of convex function, it is a convex function, right? So objective function is a convex function that is satisfied. Now the constraints must also be the convex function, then only it will be a convex programming problem. So the constraint is 5 minus x less than or equal to 0. That means x greater than or equal to 5, right? X greater than or equal to 5, or x equal to 5, you can say. Okay, x equal to 5. X equal to 5 means x equal to 5, we have like this, we have x equal to 5. So in this case also, if you consider any pair of points on the graph x equal to 5, and if you again join the 2 points, then you will get the line segment that exactly coincides with our graph f of x equal to 5 graph. So in that case, you can conclude that it is again a convex function. So you can conclude that this is a CPP, convex programming problem. Okay, so he's telling that the examiner is telling me to minimize x subject to 5 minus x less than or equal to 0. So let us find out it graphically. So it is very easy to find. So f of x equal to x, I have drawn it, the line, and f x equal to 5 is the constraint. So x greater than or equal to 5 means this region, and you will get, okay, all these regions like this. Okay, so and yes, we know that to minimize the minimum value of x in this region subject to x greater than or equal to 5 will be this point, exactly this point, that is x equal to 5, this point. So it is very easy to find out graphically for this problem, our example problem. And again, this is a CPP, right? So how to solve this, we will do it. So that means we have we are assuming that the for the penalty function method to apply, you have the unconstrained we will solve for x, okay, and that we will get some solution, and that solution, for example, we got the solution x equal to 1, you got it, solution initially you will got it. So x equal to 1 means, and this violates, x equal to 1 violates this constraint x greater than or equal to 5. So that is been violated, right? Or this 5 minus x less than or equal to 0, this actually not x greater than or equal to 5, this is our standard form, right? Gj of x less than or equal to 0. So this constraint is got while. So in that case, what we will do, we will go for the exterior penalty function method. So this can be applied to this problem. Okay, and since this is in the standard form, given by the equation, the standard form of CPP, okay, given by the equation here, or the standard form already we have discussed. So just refer that the standard form, and we have f this x, f of a capital X equal to x, and g of capital X is that means less than or equal to 0. That is nothing but over 5 minus x less than or equal to 0. So in that case, what we will do is we will add or augment or we will append the penalty function and we will formulate the unconstrained, a sequence of unconstrained minimization technique, and it is notated as phi of x, again function of x, and we are introducing the new variable, that is penalty parameter, and rk, that is equal to rk, and here it is r1. So that's case for k is equal to 1, and x plus r1, you will get r1, and sigma j equal to 1, you will get it as 1. So we will get g1. So this g1 of x, that will become g1 of x to the power q we are taking as 2. So that means x plus r1 into maximum of 0 and 5 minus x squared. Okay, so that means we have this equation phi of x comma r1 is equal to x plus r1 into max of 0 comma 5 minus x whole square. Okay, on appending this penalty function, okay, what, and we will proceed with our unconstrained problem. Then what you will observe is, first of all, the phi looks like this. Phi is function phi will be like this. Okay, so some value of r, for example r, let me take it as 1, r equal to 1. So for r equal to 1, our phi will be like this, phi of x r1 for r1 equal to 1 will look like this. Okay, and if you increase the value of r1, and the minimum of this phi, okay, minimum of this phi will be here, this point. Okay, and subject to this constraint x equal to x greater than or equal to phi minus x less than or equal to 0. So it will be this point. And if we increase r1 for r1 equal to 10, if you increase, you will get the phi function will looks like this. So our new solution will be this. So in that manner, if we increase r1 to infinity, so what happens is this phi will coincide with this minimum value 5, x equal to 5 point. Okay, so our objective, so we got the solution from our graphical uh, method. We got x equal to 5, and we found that we proved that if you if you do in the penalty function method, where this phi new function, okay, the new problem formulation will include the phi, okay, and this phi will, as the value of r1 is tending to infinity or a higher value, then this phi will converge to our original problem solution original problem solution original problem solution, which is f of this minimize x, this problem original solution original problem. That means this phi will converge, as this r1 tending to higher values, this will converge to the solution of the original problem. Okay. So in order to show that, we have taken this example. Okay, and in the next class we will actually solve by using this exterior penalty function method. We will solve a problem. Thank you.